and this is equals to d over dp of d2y over dx square and dp over dx. So again you can see this quantity which is over here, you have to differentiate it with respect to p, and this quantity that was equals to 1 over h, so one more 1 over h will be there. On taking over here it gives you 1 by h cube, and inside this term doesn't contain any p, it is giving you 0. From here we get delta 3 y0. From the next term it gives you 1 by 12 inside 6p square, this is 12p minus 18 into del 4 y0. You can simplify it of yourself, and from the last term we get plus 1 by 12 inside this gives you 6p square 24p and plus 21, and delta 5 is outside. So this gives you the third formula. So far we have derived three formulas: first order derivatives, second order derivatives, and the third order derivatives. So you have to keep these formulas in your mind. Now after deriving these formulas, there will be three more formulas regarding these three: first order, second order, and third order derivatives. And these are basically the different cases. Basically the case is only one whenever we deal with all these formulas. If we put p is equals to 1 in all these formulas, what will be the change occurring? So this is the thing we have to understand. I'm going to make a change in these two formulas because I have erased the first order formula, although we should start from the first order, but still second order and third order on board. So we'll be making a change in these two formulas directly without writing the first order derivatives formula. You can do it of yourself in the first order derivatives formula by yourself by doing the same step. The case here is when we take when p is equals to 1 and p is equals to 0. If we take p equals to 0, p is equals to 0. When p is equals to 0, if you remember, in order to find out the formula to p, we know that x minus x0 over h is the formula for the Newton's forward difference integration, and this p can be 0 only when this numerator gets equals to 0, and this can only be 0 whenever x is equals to x0. So this tells you that the value which you are looking for is lying at the point where we are going to differentiate. Make it clear that the value where we are going to differentiate is the same point, because these are two equal quantities. So that's why p will be equals to 0. On putting p equals to 0 in this formula or in the first order derivatives formula, so we obtain three more results. So we'll be obtaining three more results because this is already present on the board. So I'm making a change here on putting p equals to 0. What do we get? For putting p equals to 0, we get d3y over dx cube is equals to 1 over h cube delta 3y0. This term will be as it is. Over here this gets 0, 18 over 12. So whenever you simplify it, we'll be getting 6 over 4. 6 over 4 or 3 over 2. And delta 4y2 or y0 is there. Similarly, over here, whenever we take p0, this quantity will be 0, this quantity will be 0, and here we have 21 over 12. So 21 over 12 is over there. On simplifying, this gives you 7 over 4, delta 5 y0, and so on. So this becomes your formula whenever you take the value of p is equals to 0. Okay, now if we do the same thing here, on putting p is equals to 0 in this second order derivatives formula, so what do we get from here? So this p will be equals to 0, only minus 1 bit. So this sign will be changed. So let's change this sign only. So the formula takes the form on putting p is equals to 0 for this term. Over here, these two terms will be getting 0, so I am going to erase them from here. And the remaining will be only 11 by 12. So 11 by 12 times delta 4 by 0 is your next term. Coming over here, we get these three terms gets 0 due to p is there, and the remaining will be only minus 10 over 12. So minus 10 over 12 can be simplified in the form minus 5 over 6, and then 5 over and so on is the required value. So here we have three more formulas. You can do the same step for the first order derivative dy over dx. So the formula which we have derived for dy over dx, just put p equals to 0 at all the places and simplify. You will be getting the first formula. From the second order derivative we got the second formula, and from the third order derivative we got the third order formula. So here we collectively have 6 formulas, and 3 are the formulas which contains the values of p, and 3 without p. And you can see here, no more p's are here, no more p's are here, while in the previous 3 formulas you have observed we have used the value of p there. Now after writing all these 6 formulas, the next step is, of course, to apply them on solving the question. Because we are going to differentiate, the simple idea comes in the mind, whenever we are going to differentiate something, so there should be some function, and we have to differentiate it with respect to the variable required. Here you will be provided only the set of points. There will be no function given to you. You shall be given only a set of points, and you are required to find out the rate of change at a particular place. So how we can do it? We can use these formulas. So let's demonstrate the whole theory which we have so far covered through a simple example. So I hope you have noted down, and now we move to towards solving a simple question. So let me read it all from here. Okay, children. Now the next step, as I told you, we have to solve the question. The statement of the question is, you are given a set of points, and the set of points are x and y, 1.5 to 2.5, 3 and 3.5 and 4. And the corresponding values are 3.375, 7, 13.625, 24, 38.875 and 59. So this is the set of points given to you, and you have to measure the rate of change at x equals to 1.5. So here you can see the rate of change where we are looking is the same point, which is your x0. So here, whenever the point where you are finding the rate of change and it coincides with the value of the initial value of the given set of point, because here we have to use it. So this will be x, this x will be equals to this one, and this x0 is equals to this one. Both are same, so p will be getting 0. So here you can understand which formula we have to use. And second, as I told you, because we have derived so far the formulas by using the forward difference interpolation, so the forward difference are generally used for those values which are close to the initial set of points. So that's why we are using the forward difference here, because the value is very, of course,